Tomorrow we'll have a summer projects meeting in this room. I don't know how long it'll last, probably maybe an hour, might be a little more than that. But what we'll do is get organized. I'll tell you a little bit about how it's going to work and over what time period, and my model of how we'll interact. And we'll get organized. I'll do a Piazza account for the summer projects, labeled summer projects, okay? And that'll let me send you broadcast emails to everybody. And what I do is when I'm coming in, I usually come in on Fridays, but because of room scheduling or my own schedule, it might be a Thursday some week or whatever. But what I do is a day or two before I come in, I'll send emails to everybody on the Piazza list. I'm coming in such and such a time, date, and I'm going to talk about the following things. And I always encourage you to talk too, okay? My model, what I'd like to see happen is that I'll talk about the things I'm working on this summer, and I'd like to have you guys talk about the project you're working on. And it's a really nice opportunity to get some feedback. Think of it as a design review, a friendly design review. So you get up and you talk, present at the board, and sketch out stuff, or whiteboard. Or it doesn't have to be formal. You don't have to have PowerPoint slides or anything, but present your design. Lay out a package diagram or class diagram, or show us some snippets of code or whatever, and get feedback from us. So I think that's well worthwhile for a couple of reasons. One is it helps you. It's still part of the learning process, the learning process for design, but also it's nice practice for an interview, because it's going to be the same kind of thing that'll happen to you in an interview. They'll say, all right, stand up to the whiteboard, and you've listed this project on your resume. Tell us a little bit about it. And for an interview, you always want to have a 30-second presentation of your project. It's called the elevator pitch. You're going upstairs in the elevator and you're telling somebody about your project. How do I, in a very few 3 or 4 or 5 sentences, give them the core of the idea and why you're enthused about it? And then a 5-minute, somewhat more detailed presentation, and a 30-minute presentation. You should be prepared to do elevator pitch, 5-minute presentation, 30-minute presentation on every project on your resume when you go in. Okay? If you can't do a good job with that, you're on the bus. Okay? You're not going to get the job. So anyway, I'm going to be I have, if you look on the class account, I have 2 communication systems. I have the one you've used, the message, asynchronous message passing communication. I also have an HTTP client server channel that is a work in progress. It's not completed, but it's far enough along because it's HTTP. I can talk to Chrome. And, I can't do. It's not a full-up server by any means. Okay. I'm just doing very, very simple things, but it's showing you that the protocol part is working. And one of the first things I'm going to do this summer is merge the 2. I would like to have a communication system that is message-based, can be used to do HTTP communications with browsers or with the Java HTTP, Java components, for example. That makes a nice way to do cross-technology interoperation. Okay. But I don't want to just do HTTP, which is a synchronous communication. I want to be able to do asynchronous communication too. And so, I'd use a one-way attribute to tell it. If I don't have the one-way attribute, I'm going to wait for a response. server, it's your job to give me the response. And if I have one way, then the server's going to ignore me. And so on my channel, I have both the client and the server, the sender and receiver, okay, just like the channel that you've used. So what I'm trying to do is merge those two things, get the best of both worlds. And also take the editorial red pencil, go through it, and get rid of all the cruft, anything that was, you know, there's always in some fairly major design some stuff that you did and then you did, well, it would have been easier. Next time I do, I'll, you know, that sort of stuff. And after I've done that, I'm going to go back into a repository, just like you're doing for Project 4. I'm going to build a repository the way I think it should be built. And, you know, play around with what I think the graphical user interface should be. It certainly would have a navigation view like I have, but I've been playing around a little bit with the tree view for that. Tree views are interesting because the naive implementation of a tree view control is wrong way to do it. If your model is, oh, I'll trundle down to the directory and get all that stuff and build my tree view, it'll take 2 minutes before the application comes up. What you want to do is just whatever your starting path is, you want to analyze that path and the next level down so that you can set up the tree view. And then when you click into something, you analyze the next level down. You click analyze the next level down is that's the way it should work. And it's a little, you know, not hard, but, you know. So, you know, and I've got a bunch of things on my agenda. Another thing on my agenda is to, a lot of things have happened with templates from C++ 11 to 14 to 17, and I want to look at them more carefully myself. I've got a really nice reference for that, which, by the way, I need to put on this page. I'll put a reference to that on this page. But anyway, I will probably plan for the summer project meetings to talk about a little bit about my project, what I'm currently working on, but also probably a little bit of the template, the C++ 17 and 14 template ideas, things like that. So. But anyway, that's what's going on in this. So we're going to have a summer, the upshot of it is we're going to have a summer projects meeting. If you're not going to be here, you could still come to the summer projects meeting if you want to, with the intent that you're home with your family or you're at some, doing some internship. Initially, the first couple of weeks of your internship, you're going to be so busy, you know, you won't do anything else. But later on, you probably will have a little time, and so you might choose to work on one of your projects, polish one of your projects up, and, you know, be on the mailing list, you know, so you could use Piazza, and, you know, if you got questions or, you know, things you want to talk about, you could do that via Piazza. So. You're all invited. Anybody that wants to is invited to come tomorrow afternoon at 1 o'clock. Okay, let's talk about template metaprogramming. So template metaprograms run at compile time. The specifications for templates are such that there has to be a programming language that the compiler implements at compile time, that the compiler uses to do its job at compile time. It was discovered accidentally, so the story goes, I don't know whether that's true or not, but the story is it was discovered accidentally that you could actually write programs with that language, and people started to get interested. Template metaprograms are not something you're going to do every day. They're a little weird, as you'll see this morning, but template metaprogramming is used a lot by library designers. I have already used it a little bit, and will use it quite a bit more in the libraries that I'm working on. but also they're used to implement some functionality that would be hard to implement any other way. The tuple is implemented using some of the ideas we're going to talk about this morning. We're going to talk about type lists toward the end of the lecture this morning, and the tuple implementation looks very like the type list implementation. I'm not going to talk about it this morning, but I probably will talk a little bit about it next week. And then finally, template meta programs are also used to exchange compile time for runtime by doing things like loop unrolling. So, but anyway, we'll see a little bit of that sort of stuff. So, so my claim is that there is a programming language, in fact, a Turing-complete programming language that is available to you because of the, in C++, because of the template mechanism, and that program runs at compile time. So, as a prelude, I want to just remind you of a couple of template things. Remember that templates do type deduction, and there are cases where they don't. The first two examples, the first two things I'm going to talk about this morning are cases where it can't do a good job or doesn't. So if I have a template type that is just appears as a return type, the compiler doesn't do type analysis, type deduction on that. For one reason, because clients aren't obligated to use a return type. They can just call the function for its side effects, if it has side effects. So, so what we have to do is we have to, for template functions particularly, we have to tell the compiler that the return type is this type X. And you know, you could say, yeah, but it could look at this expression and look, examine this entire expression. It could deduce that that's what the return type has to be, but it doesn't do that. You know, it's just looking at this particular part. You know, it's not doing a whole bunch of detailed semantic analysis or syntactic analysis. So anyway, for the return types, you have to tell it. Now, for templates that have maybe a 2 argument types and return types, so there's 3 types. So there'd be types in, you know, passed as values of different types passed as arguments. The compiler can do type deduction on those because it already knows the types of the things that you're passing. So its deduction works fine. So if I was passing arguments, I'd have the option. I could list here all of the template types, X, Y, Z. Suppose Y and Z are types of the arguments. I could say x.clone of x, comma, y, comma, z, and then pass it the arguments. But I could also just say X, and the compiler is smart enough to say, this is just the return type, this is just the type, the unmentioned type, the type that is mentioned here for the deduction. So that'll work either way. Another case where the compiler doesn't always get it right, type deduction, is here. There are times when the compiler sees something like this and it says, is this a type defined in the C class, a nested type, for example, or is this a member of the C class, a static member of the C class, for example? Now, you know, deeper syntactic analysis would show you that this has to be a type, okay? Because this declaration doesn't really make sense if it doesn't. But the compiler doesn't do that. And you get, what happens is you get a error message that says dependent name iterator is not a type. And that's a giveaway that all I need to do is preface this with type name. And same thing here. Now it turns out that type inferencing has been getting stronger and stronger. We no longer have to do this. With C++, with Visual Studio 2012, you had to do this. I think since 2015, you didn't have to do this here, but you do have to do it here. So there are a lot of cases where you have to give the compiler a little help for its type inferencing. And you'll see a few places in what we talk about today where I've done that with type names. In at least one place in what we're going to talk about, I'm going to use template parameters. So let's just take a quick review of that. This happens to be a class in which I want a class to create an object, and I have different policies. And one policy would be to create it by cloning, by making a copy of an existing object. And there's times where that makes sense. And so, I have this class clone, and I have the created type, and now here for the creator, template class created, class creation policy, this creation policy really ought to be templatized on created. And here I've allowed the possibility that a user doesn't templatize it on the right class. Okay, that's not a good thing. Certainly can be made to work. So here, if you do it this way, creator of created type, clone of created type, then it will be correct. But I could, a user who didn't understand what was going on could perfectly well use some other type, and it might compile and run, but be incorrect. Hopefully it would fail to compile. Usually it would, but it might compile. No. So, and also, you'd like to not have to have that additional. So we use template policies for that. And they look this way. So here's the clone class, just like before, nothing's changed. The created type, just like before, then nothing's changed. But here in the creator, now I have template class created. Now I have a template as a template parameter. So it's a template parameter. I have a template as a template parameter. So here I have template class created, class creation of policy. Okay. And now it's clear, because this is the same as this, okay, it's going to be correct. Creation of policy will be templated on that one. This is still a parameter because this is a parameter, but now it's the same parameter. Okay. And so now when I use it, now I can say creator of created type and clone, and I don't even have to say that it's templatized on that type. Okay? So template policies are used to handle that situation where one of the arguments is templatized on another argument, and you want to make sure that it's templatized on the right one. Okay. Lastly, there are a place or two where I'm using partial template specialization. So just as a reminder, template specialization is any time we narrow the parameterization. So we have a template class. One example is I have a template class of a single argument t, and then I specialize it for t stars, for pointers of t. The specialization is a narrowing of the number of possible object, the types to use there. Here's the other case where, in this case, I have two parameters, type t and int, and this happens to be a smart pointer that points at arrays. And it has member functions for indexing through the arrays and so on. And now I have a smart pointer that is templatized on 1. It's a specialization now. Instead of having an arbitrary size, now I have a fixed 1. That's a specialization. And now it wouldn't make any sense to index it, so I just leave that code out. This is a different class. Two classes, templatized classes with different arguments, they're different classes. So, template specialization. Okay, so with that reminder, let's start talking about template metaprogramming. So I want to start with a little example. So binary conversion. To understand what's happening here is I'm going to start with a decimal number, an integer, that could have any normal integer values, but what it has is all its digits are ones and zeros. So it looks like a binary number. It's a decimal number that looks like a binary representation. It is a representation for that binary number, okay? Now, I am going to calculate an integer whose value is the decimal value of that binary. So if the ones and zeros were really the digits in a binary number, what I'm going to calculate is the value of that binary number in decimal. Okay? And the way it works is I define template unsigned long n. So n is this 1001110 or whatever. Okay. Struct binary, static unsigned constant value equals binary of n divided by 10 of value, shift to the left, and now I take modulo n. What I'm doing is, if 0 was the last one, okay, what I'm doing is I'm lopping off that value, okay, and setting it to either 1 or 0, depending on, modulo 10, in this case is, because I'm using all ones or zeros, is either going to be 0 or 1. So, okay. And now, this is recursion. I'm evaluating binary in terms of binary. So now, that recursion will go on until I reach this is a specialization, struct binary of 0. So what I'm keep dividing n by 10, and eventually, I'm going to get to 0. And so when that's true, the language guarantees me that if my template argument satisfies the specialization, it will use the specialization. So that stops that evaluation. Okay? So, so here's the way it works. So let's just run it. Whoops. Let's just run it. So, understand, these are really decimal digits that just happen to look like binary numbers, okay? And then I'm calculating their values, and you can look at it and say, yeah, that's correct, okay? So, but all that calculation happens at compile time. If I so here in my main, I'm citing each of these and displaying them If I just said binary 1, 1, 0, all the ones leading up to it would be evaluated, just not displayed. And the way template metaprograms work is all the calculation is done at compile time, but you can't see the results until runtime. The results are stored in value. So what's value? Value is this static unsigned int. It's constant, you know, static unsigned constant. So so that, you know, what I've done, each time I'm recursing, that value is saved. I'm not overwriting it. I write, so these are each separate functions that are, you know, going to wind up being in code space. They're all there. Every one of these iterations are in code space, okay? And so, you know, I go down, I can't evaluate, now I can evaluate it, it does, and it pops it up and evaluates the next one, pops it up, evaluates the next one, pops it up. So they're all there. So what happens is, if I just cited one of them, I'm going to go, you know, and calculate every one up until I reach that stopping condition. The other interesting thing is that if I remove this, where's my, here it is. If I remove those, what do you think will happen? Oh, okay. So that wasn't what I wanted to illustrate. So what, you know, if it wasn't for the fact that I hadn't, okay. So normally what will happen is with a lot of these, you know, when you remove the stopping condition, it recurses forever. And so eventually you'll get a compiler internal error 300 that says you blew the stack. Okay. I tried it on another example at 8 o'clock, and what happens is it ran and ran and ran and ran, and it was you know, understand that it's calculating all this stuff, filling up memory. So it'll probably, the compiler will start running slower and slower because it'll start to fault, page fault, page fault, page fault, because what it's building is bigger and bigger and bigger. So anyway, didn't illustrate when I wanted to, but so you say, okay, but that's just a little trick. So let's try to you know, build some more interesting functions. So here's a function. Square, and this doesn't need to recurse at all. It's just value equals I times I. And this calculation happens in compile time. In order to write the code for this, it has to be, the compiler has to be able to interpret this and evaluate it. It's doing an eval on those, okay? And so it'll display it. And I have a power. Now this is recursive. Power uses the fact that if I have n raised to the p, that's the same thing as n times n raised to the p minus 1. So all I'm saying is value of n raised to the p is n times power of n to the p minus 1 value. Okay. Now enum, so what's going on here is value is just the name. An enum is a named static constant. Okay, and so this is just a named static. This could have been. I could have done this as a, just like I did in the example before, as a static constant int. That would have worked just fine too. but enums are static, and because of rules that used to exist on the compiler, you had to use enums, so a lot of the examples you'll see use enums. And I have to have a stopping condition. Anything raised to the 0th power's value is 1. So that's all that's necessary. So, I'm just recursively calculating that value. And so now here I say, square of 9 value, power of 2 to the 16th value, so let's run it. And sure enough, square of 9 is 81, and 2 raised to the 16th is 65,536. So, and it's correct, by the way. I've sat with the calculator just to make sure it was correct. Okay. Okay, so there is an extension which I haven't illustrated here. I can declare, if I declare a integer as const expression, CONSTEXPR, that's equivalent to saying it is a constant static value, meaning its compile time, can be evaluated at compile time. Now, I can declare something as constant expression and then assign it a value that is only known at runtime. And that will compile and it will be evaluated at runtime. But if I assign it something that can be evaluated at compile time, it will be evaluated at compile time. I can declare a function as constant expression, as a qualifier on the return. And what that means is that that function, if its body is all known at compile time, then it will run at compile time. If its body isn't known at compile time, then it'll run at runtime. It's kind of nice. So that, this, being able to do stuff like this is a question of, can I be tricky enough and imaginative enough and brilliant enough to come up with some scheme for calculating this thing that I want to calculate? But it can only be, a function of things that are known at compile time. Its arguments known at compile time, and the data. There are no such thing as a variable. They're all constants, but it's the way I modify constants is just like a C# string gets modified. The C# string is immutable. If I want to change it, I create a new C# string with a modification, and it's exactly what's happening here. In these recursions, I define this first one, then I modify it, so I've defined both of them, and they're just static constants. And they're being stored in static memory, just like any other code. So I can do functions, sort of. But you say, it's not a language, you can't do loops. Well, of course you can do loops. I wouldn't have posed that question if you couldn't. So here's how you do loops. Here's a simple loop, the simplest. Template int I. Now, you can provide integral constants here. Perfectly okay as a template argument. That's allowed. Class loop, static inline void exec. This is just a function in this loop class. And I can only, if I want this class to be defined and run at compile time, it can only have static functions. It can't have non-static member functions because you can't have variables, okay? And I can't have, there's no this pointer. This pointer doesn't exist at compile time, only at runtime. So they have to be static member functions. And now my calculation is just to display this integer I. and then loop of I minus 1 of exec. So you can see, in order to evaluate this, I got to evaluate this, which means I got to evaluate this, which I evaluate this, until I hit the stopping condition, loop of 0, and then I just say C out of 0. And you say, but these statements are runtime. What do you mean this is a compile time loop? What I mean is that these cout statements, what I'm doing is I am writing into my code memory cout 3, cout 2, cout 1, cout 0. Okay? And then when I run it at runtime, I execute those cout statements. That's what's happening. So this simple loop, and sure enough, it works. So here's the first part of it, loop 4 of exec 4, 3, 2, 1, 0. Yep, okay. So we can loop. Now the next one just makes that a little more flexible. So here I have a template in class B, struct 4. So now I have a static void function iteration taking an I, and now on this B class I'm calling its static function, I can only call static functions, body of I, okay? And now for n minus 1b, iteration I plus 1. So if this was 0, now this is body of 0, and now this is 1. So now I got to go back and evaluate iteration again, recursively, okay? And here's my class B. No, I'm sorry, this is a stopping condition for 0b, static void iteration int of I. And so because I didn't say 4 of n, I'm not recursing. I don't have any recursive call here. And my class B is, I'm just printing out I. So I'm not really doing anything different than the loop. I'm reversed the order. But the model is I've factored it into two parts. One is the looping part, and the other is the part, the body function, which is where I'll do whatever I need to do. You know, anything that I can do with compile time constants, any calculation I can do with compile time constants, I can do in that body. And those constants can depend on these arguments. I mean, they're constants from the compiler's point of view, but not constants from the user's point of view, because in my program, I can change the template argument. You know, I can change the first argument to be whatever I want it to be. So, so now I mean, it's going to do the same kind of thing, but it just has factored it out in a way that makes it a little easier. So here's 410b iteration of 0. I start at 0 and I go for 10 of them, and I'm just printing out, you know, those integral values. For 8b iteration 2, so I start at 2 and now I have 8 of them. Okay, so you know, it's a little more flexible as far as looping. And my B can actually do anything that I wanted to do, you know, that I can figure out how to do at compile time. The next ones have to do with accumulation. So here, what I want to do is I want to build up a sum of something. So int n template int class f. So this is a template parameter. And I want f to be templated on an int. And so enum value equals accumulate n minus 1. This is my loop coming. Value plus f of n of value. So this is the sum, and this is the term I'm adding to the sum. So f represents the term I'm adding to the sum. Okay? And I have a stopping condition, 0, okay? So I just take f of 0 value. And now here's an f. Here's an example of an f. Struct int n struct identity. So f has to be templated on int. So template int n struct identity, just value equals n, whatever that is. Here's another one, struct int n struct of square, num value equals n times n. Okay. So in one case, I'm summing up. So when I run with identity, I'm just adding 1 plus 2 plus 3 plus 4. When I'm accumulating on the squares, I'm adding 1 plus 4 plus 9 plus whatever. Okay? And sure enough, we see that the answers are 10 and 14 as they should be. So, hey, we got loops. And you said, yeah, but you don't have selection. So let's go select. So here we have template bool p class t class f. And the model here is, if this is true, we want the behavior of class t. T for true. If this is false, we want the behavior of class f, f for false. So t is the behavior we want if the predicate is true. False is the behavior we want if the predicate is false. Understand the predicate might be, is this Windows, yes or no? Is this Windows or is it Linux? Okay? Now that gives us the opportunity to do some setup based on the platform. So in our library, we're writing a library that wants to support programs on Windows, another library to support Windows on programs on Linux. You've already seen a little bit of that from me. My file system, I have a version for Windows 11. So if the setup's a little, this gives us the chance to do that setup depending on the platform we're on, okay, without the user have to do anything. So, and I have a class 2 true type, which is the behavior I want if it's true, and I just print out, I'm running on Windows 10. And my false type says, I'm not running on Windows 7. Okay? And so here I say constant expression bool, I'll come back to that in a minute. Windows 10 equals true, Windows 7 equals false, and now select Windows 10, first dot say, select Windows 7, second dot say, and so sure enough, I'm running on Windows 10, I'm not running on Windows 7. And you say, yeah, but you knew what the answer was going to be. But understand that what I'm wanting to do is to do a platform-specific thing, for example. Just set the switch, and if the switch is for Windows, so I know, so now that opens the opportunity for doing something like there are defines that say this is Windows. And so you're testing against that define. You're selecting on that define, for example, something like that. So that gives you the opportunity to set things up for different platforms. Or, just maybe it's just a different model. Maybe I'm doing an optimization program and I have several different optimization algorithms. Steepest descent, gradient, steepest descent, conjugate gradient, blah, blah, blah. But there's a whole bunch of different steepest optimization algorithms. And so now, just by setting a compile time constant, I can do a whole bunch of setup at compile time, if I need to, maybe deciding what elements will be compiled. All right. Yeah, but you don't have switches. Yeah, we got switches. Set a startup. So this is like a generalization of the selection. So here, I have class, this is the generic one, class int case, switch, static inline const char star result, return case default, and then this is a specialization on switch 1. I have case 1, switch 2, case 2, switch 3, case 3. And now, here's the cases. I just illustrating them. And now, I could calculate. I want to select on the case 2, and so I just say switch of select. And this last one, I switch on 22, which isn't any of these, just to show that if I don't take one of the specializations, 1, 2, or 3, then I'm going to take the default case. So let's just run it. So it's like the other case, but now, I've got more platforms. Now maybe my platforms are Windows and Linux and Macs. So I want to select on those cases, or I've got some large set of algorithms that I want to choose between and do compile time setup for. There are a lot of things that are done with traditionally have been done, set up for different platforms with very awkward pound defines that get a whole lot more manageable if you do them with template metaprogramming. And you say, okay, so my claim is, I started out by saying that there's a programming language, in fact, a Turing complete programming language. You say, but you don't have any containers, no lists. We do. We have type lists. So now, our type list, the model here is that H is the head of the list, and this is a type that represents all the others. So in truth, what this is going to be is head is a type, and T is a type list. So we're defining a type list in terms of a type list. Surprise, surprise. Recursive definition. Surprise, surprise. Okay. And we have a null type. And I'll show you the slightly more modern versions of this I did in another. And we have an empty type. And now our list looks like this. So here, using type list 1 equals type list of int and null type. So here's my head and my tail, and so these are just two plain types. Okay? So I have a type list of one type, int. And now I'm going to declare, here's my int val equals 1. Okay? Now, I can extend that to a type list of two elements, two types. So here, using TL2 equals type list of char TL1, what I used before. So now I have a type list of char and int. And so my head is char value of A, and I could have said, just like the TL1, there's a way to sequence back down, which I'm not doing here. I'll show you. There's a better type list coming. You'll see some of those details there. And now, TL3 type list double TL2, just recursive definitions. So sure enough, I have a list of types, and I can then declare values for all those types. And you say, okay, but that's not a real type. You know, we can't append to it. We can't insert something. We can't remove something. So here's our same old stuff at the beginning, you know. Now instead of type defs, I'm using a using. And here instead of making my constructor private, I make it public delete, okay, for both the head and the tail. That just means I don't want to be able to manipulate this type. It's just a null type, just a fixed entity. Empty type. And now there's a type list. So this material, this better type list, I stole from Andrei Alexandrescu, who's the author of Modern C++ Design. I'm going to talk about him a little bit at the end of this when I'm done talking about this. He's an interesting character. He, in his book Modern C++ Design, he developed a Modern C++ Design was all totally focused on templates, including some metaprogramming. And he defined 30 type lists. So here's a type list. I'm defining a macro, type list 1 with 1 type, type list 2 with 2 types, type list 3 with 3 types, type list 4 with 4 types. And notice this is just a recursive definition. Okay. He defined 30 of them in a library called Loki. He wrote this library, I'm sure for 2 reasons. One, to make sure the code he wrote in the book was correct, but then for people to use to help understand stuff as they were reading through the book. And Loki, by the way, is the name of the Norse god of mischief. Remember the movie Thor, the guy with the big hammer? His half-brother was Loki, the mischievous, you know, evil counterpart. Well, that's the Loki library. So this guy, Andrei Alexandrescu, has a great sense of humor. So anyway, he had a huge list of them. I've just duplicated the first few, just to show you. And now you can make a type list. You know, so by default, these are all the null type, so, you know, you'll declare them just whatever types. So, you know, any types you don't use, they'll just be the null type. And so now I have a type def, type list, make type list, T1, T2, T3, T4, you know, and so on. And, you know, and the specialization. So I have this facility for making type list. Now, length. I can find the length of my type list. And the model is that I simply recursively walk down the list until I get to the end, incrementing. You know, you've seen me do something very similar to that already, just incrementing a counter. So that's what we're going to do. You know, we stop when we get to 0. You know, and here we're just, you know, value equals 1 plus the length we computed so far. We just keep adding 1 to the length that we've computed so far. And when we get to 0, then we stop, and our count is the length of the list. So we can evaluate the length of this type list. We can find the type at some particular index. So again, same kind of recursive structure. Now we just keep walking down the list until the type on the list is the type that we're trying to find. We're trying to find the index of a given type in that list. And the nice thing about it is that the way we've designed it is that if that type is not on the list, it'll return -1. So you know if it wasn't there. So we can find the length of the list. We can find the index of a given type on the list. We can, I'm sorry, so here, I'm sorry, this first one, so the words I used were for the next example. This one is just finding the type at a given index. So you give it the index, and you just keep recursing down. And when you get to that index, then you return that type. That's the type of that index. And this is finding the index of a given type. It does what I said, it's searching iteratively down the list until the type match, and then you return that index. And appending another type, walk to the end of the list and append it. Appending, so, you know, replace type in a type list. So, you know, all same basic idea. I'm just getting this iteration of work and doing whatever's necessary to make that work. So, so now, if we run this, so I just started out with this simple example, the same example I used for the simple type lists. And now I'm measuring the length of, so you know, I define these recursively, TL1 for A in terms of TL1, you know, and so on. And so the length is 4, the length is 3, 2, 0, 1, 0. And now I can make a type list. Instead of doing this manually recursively, I can use the macros, and that's what I'm doing here. Type list TLF, int char double class. I'm just using that make. I'm inserting the types and using that make. And the length of TLF is 4. Demonstrate indexing and searching in a type list. Type list TL4, I'm displaying it here. Type at index 1 is char, so here's 0, 1, sure enough, the type at index 1 is char. Index of double is 2, 0, 1, 2, sure enough, the index of the double is 2. Okay. Index of long type in TL4 is -1 because there is no long. Demonstrate appending to a type list. Now I'm going to append a long to TL4. Now the index of long type is 4 because I appended it. So now it is on the list. Demonstrating type replacement. Replacing double in TL4A with short. So index of short in TL4 is 2. That's where the double was. And now index of double is -1. Doesn't exist in the list anymore. So I can do at compile time all the kinds of things you would normally might want to do with a list. This is a Turing complete language. Can you easily program anything? No, you can't. Okay, but if you looked through the code in the, which you can because it's all template in the standard template library. Most of the standard library is templates, but especially the standard template libraries, of course. You can look at the source code. You'd see that a lot of what's happening now is the template metaprogramming is being used in the library to do stuff. Tuple is done with template metaprogramming. Tuple is created in a way very similar to this type list. If you look at the tuple code, next week, about the only thing left I'm going to talk about is how tuple is implemented. We'll see that it's implemented very like this type list. So that code, really familiar. So template metaprogramming is used in libraries to build things we couldn't build any other way, really. Okay, it just has to be done that way. Tuple really has to be done that way. And you know, the accessor in tuple, the get function in tuple, is very like our type at, you know, very, find the index of that type. Code very, very similar to that. So it's used to build things that would be really hard to build any other way. It's used to one way it's used is templates tend to give you, when you make errors with templates, they tend to give you very unreadable error messages. And the reason is that they're burrowing down into the guts. You know, the compiler is doing a whole bunch of type inferencing down, 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 and when it discovers that it can't do that type inference, it's several layers down and is giving you error messages at that low level that don't mean anything to you up here. It was stuff it was doing that you don't know anything about as part of its type deduction process, and when that fails, it's giving you error messages about that. They don't mean anything to you. Really hard to psych out. So template meta programming is used, I'm going to show you in my next example, give you some ideas of how that might be. It's used to try to make things fail earlier so you get more reasonable answers, more reasonable error messages. It doesn't, it's not changing when things fail or avoiding a failure. What it's doing is making it fail quickly so that you get much more reasonable error messages. There's something called concepts that Bjarne Stroustrup, the creator of C++, has been pushing on a long time. The concepts are very like C# constraints. So when you use generics, if you want to call a function on that generic type, it won't let you unless you prove to it that that type has that function, and you do it with an interface. So you say you're constraining this type has to be derived from this interface. That's a constraint. And C++ is working on concepts which are really just like those constraints. The idea is, again, it isn't going to make things compile that wouldn't have compiled in the past. It's going to give you really good solid error messages. And also, it helps document what the designer expected, so the user of the class can look at the constraints and say, oh, this type has to have these properties. Now I want to look a little bit at types. This is starting to get at these are type detectors. And we're going to go, at the end of this, we're going to go look at that and come back to some of the points I was making before. This is a test to see is this type T a character? So struct is char enum value equals false. The generic case says no. I don't care what the type is, the answer is no. But it's specialized on char, which gives you a yes answer. And so it's just using the C++ guarantee that if the types match the specialization, it'll pick the specialization. So nice test to see if something is a character. Is this an array? Is this type an array? So is array, the answer is false. Oh, but if template type name A, int n, struct is array A of n, okay, enum value equals true. So now, is pointer. And there's obviously a whole bunch of, there's a bunch of cases, and I've looked at some. Is pointer, default enum is false, it's not a pointer. Struct, is pointer T star, value equals true. So I'm using type inferencing. Is pointer T star const, value is true. Is pointer T star volatile, value is true. Is pointer T star const volatile, value is true. So in all those cases, it'll, yeah. What does volatile mean? So that's interesting. In C# and Java, it says that I guarantee that each thread will see the same value. I will flush the caches, or I will either do a load or a store before I evaluate. But that is not what it means in C++. In C++, what volatile means is this value is an unusual number. It's an unusual address. What it really means is I'm probably looking at a port. You, compiler, optimizer, you won't see me ever change that value, but that you can't go optimize it away at its default value because it's going to change, and you won't see me change it. That's all volatile does in C++. It's used for writing device drivers when I, very platform-specific stuff. When the compiler, when the optimizer may do things we don't want it to do. Okay?
Can't we take like smart pointers or unique pointers?
I wouldn't ever qualify a smart pointer as volatile. I might qualify what it points to as volatile. Okay. But I wouldn't, so I might say smart pointer of volatile long something, but but anyway, is pointer to member by default false, but struct is pointer to member. So here I have type colon star returning u, okay, value of u. So this is true. This is member data. This is member data of type u in the V class. But also it might be a pointer to a member function. So this is a pointer to a member function. This is a pointer in the V class. This paren w means it's got to be a function that accepts the type w and returns the type u. So both of these would return true. But otherwise it returns false. Not a pointer to a member. If it's a pointer to a member, it has to be a pointer to a method or a pointer to data. And this, and so if we run this, int is not a char type is a char. I just did a, I did a using char type equals char. X3 is an array, X star is not an array. So in C++, arrays decay to pointers. If I pass an array to a function, what I have on the inside of the function is not an array, it's a pointer to the first element of the array. It's a process called decay, it's very well known. But it's not an array. X is not a pointer, X star is a pointer, cos X star is a pointer, blah, 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 I defined a class, X and Y, so, Y of X is a pointer to member, is a pointer to member. So, so I can use these in my code. Here's one situation where you might use this. So if I have I'm writing a parameterized method, and I expect to apply it to, let's say, two different types. And in one type, I have a branch that does something appropriate for the first type and would fail to compile for the second type. Else, I have a branch for the second type that works for the second type would fail to compile for the first type. That will fail to compile. Because the compiler, the template compilation, you know, when it's the second phase of the template compilation, it doesn't check that I'm only running, that if I'm this type, I will only run that type. It sees that type in two places, one of which compiles and one of which doesn't compile, and it fails to compile, no matter which type you have. But if you use one of these tests, okay, now it sees that, there is a conditional if you can use. Okay, I haven't talked about it yet, but I'll just show you quickly. Now you can make those cases compile using these type tests and a little bit of metaprogramming. Now, if I have a library template parameterized function I'm trying to write that on this branch works for these types and on that branch works for those types, A, I might want to use a type list, okay, and B, now I'll use conditionals, compile time conditionals that will make sure that I only compile those parts that are compiled. I don't attempt to compile those parts that won't compile, depending on the types that the user instantiated. So that's another place where you are likely at one time or another in your career to want to be able to use that, and if you know about it, you can use it. Okay. I've used it once or twice. I looked for it last night and I couldn't find it, so. Now, let's go back and just take a quick look. We'll get a little more idea of what this is all about if we go here to cppreference.com. Oh, I have no internet connection. Okay, let's get an internet connection. Okay. So this is what I was trying to get to. That link in the source code points to this page. So so there's a bunch of types now that get a little more specific. Is void, is this a void type? Is this a null pointer? Is this an integral type? Is this a floating point? Is this an array? Is this, we've already seen how to do some of these, but there's a big long list that are already done for you. Is enum, is union, is class, is function, is this a function type? Is pointer, L value, R value, blah, 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 blah. Composite type categories, is fundamental, is this a primitive? Is arithmetic, something I can add and subtract? Is scalar an integral type? Is object, is this created from a class or a struct? Is compound, checks if a type is a compound type. Is reference, is member pointer. Is constant, is volatile, is trivially copyable, meaning I can do a memcopy, it's blittable. Is standard layout, is pod. Pod stands for plain old data, and it means that it's a type that it's either intrinsic data, either the fundamental data, or it's a wrapper very carefully designed not to add any size to it. Okay. And I, in the past, have talked about those a little bit. It's possible. I'm not going to do a whole lot next week, as I'll explain, but it's possible. I'm going to talk about tuples, and I might talk about there's something called veneers and bolt-ins and stuff like that that relate to this. Now, other things is constructible. I have a, you know, can I construct this thing with these arguments or whatever? Is trivially constructed? Does it have a default constructor? Is copy constructible? Is move constructible? Is assignable? Is copy assignable? You know, blah, blah, blah. Is swappable with? Relationships, are these the same two types? Is T1 and T2 the same type? Is T1 the base of T2? Ah. Okay. Here's a case again where I might be writing a function that took these two arguments. I want to make sure I want this to fail to compile if B is not the base for D. Is invocable, you know, meaning it's a callable object. I can add and remove qualifiers. I can add and remove references. I can add and remove pointers. That's to the types. Okay. Decay applies type transformations as when passing a function argument by value. So what this does is decay does the same thing to the type as if I passed it by value. Okay. If I pass an R value by value, it becomes an L value because inside the function I have a name A, okay, for that argument. Common type. This is useful. So I showed you early on when we talked about templates a max template function. And you could design max with one argument, which is what I did, the same arguments and the same return value type. But suppose I wanted to allow two different types. So I wanted to be able to correctly handle the case where the types were not the same, but they were comparable, like ints to doubles. Is this int, is 1 less than 1.5? Yeah. So now I'm, say, type 1, type 2, but what do I make the return type? Do I make it type 1? Well, if I put double in the wrong place, I'll convert the double to an int, and I'll, you know, no matter where I put it. So I can't make it type 1. I can't, what do I make it? So I can make it common type. So I can return common type, and what that will do is it'll return, if it needs a double, it will return the double. If it returns, so I have these two types, and the one is convertible to the double, you know, with a simple conversion. Double is convertible to an int, but only with loss of significance, so the common type would be double. There's other ways of accomplishing the same thing. I could say as my return type, so I have this max of T1 and T2, I could say decal type of A less than B, where A less than B were in the body, which were A was T, and you know, and that would have worked too. But this is just a simple way to do it. So all of these things are related to template metaprogramming and allow us to do useful things in library code. Typically, you're not going to use these in situations, you know, in day-to-day run-of-the-mill code. First of all, you don't have the time to do that. You know, it takes quite a while to get these things right, these template metaprograms right. But if you're designing a library, it can make your library more flexible. So you spend a lot of effort to make it a little bit easier. So one guy spends a lot of effort to make it a little bit easier for 10,000 people to use. Big, big, big win. Okay, I'm going to stop there. I want to talk just a little, I can't. I wanted to talk a little bit about Andrei Alexandrescu, and I'm out of time. Meant to do that. I'll probably talk about him a little bit. I wanted to talk about Andrei Alexandrescu and the D language. So what I'll do next week is